Hello everyone, I'm Ayush Kulkarni and today we'll be talking about optimizing storage solutions and querying techniques for enhanced database management. So let's move on. What is database management? In today's digital landscape, database management is crucial for organization. This presentation will explore techniques for optimizing storage solutions and querying methods that enhance overall data efficiency and understanding these concepts is vital for improving performance and reducing costs. So, what is present inside of it is well, okay. So, first one for storage and querying in databases is storage and files structure. So, storage refers to the underlying mechanism that store data in a database. This can be thought of as the physical layer where data is held on storage media like hard disk, SSDs, or memory. The efficiency of storing and retrieving data largely depends on the structure of the files and how the data is organized. File structures are ways in which the database management systems organizes the data files on the disk. There are two ways for this, sorry, three ways for this. Heap files, which are unordered files, basically they are records that are stored randomly as they are inserted. This file structure is simple but inefficient for querying specific records as it requires scanning the entire file to locate a record. Then there is sorted files. They are sorted in order based on one or more key fields. Our Windows Explorer uses the sorted or sequential files. Then there is also a hashed files. The hash function is applied to a key field which determines the location of a record. This structure allows for quick access to records based on the hashed key. Its advantages are its fast retrieval. However, its disadvantages is that it is not suitable for a large chunk of data. Then we move on to cloud storage advantages. Cloud storage provides flexibility and scalability for businesses. It allows for easier collaboration and access to data from anywhere. By utilizing cloud solutions, organizations can improve their storage costs and improve their data management capacities. Then on-premises storage pros and cons. On-premises storage offers control and security for sensitive data. However, it can be more expensive and less flexible than the cloud solutions. The organizations must weigh the benefits and drawbacks to determine the best fit. Then, before moving on to querying, I would like to talk about the index files, single level and multi-level indexes as well, which I forgot to put in the PPT. So index files use an additional data structure called as an index to allow quicker access for records in a file. Instead of scanning the whole file to find a specific record, indexes allow for a faster lookup, improving performance for a larger data set. So there are two types of indexes. Sorry, my bad. Four types of indexes: primary index, secondary index, clustered indexes, and non-clustered indexes. So primary indexes, they are built on the primary key of a file. They have an index entry that corresponds to a block in the file. For instance, the first record in each block. And since records are sorted based on the primary key, the binary search can be performed on the index to quickly locate a record. For example, if you have a file where the employees' IDs are sorted, you can index the file based on these IDs for faster retrieval of data. Then moving on to secondary index, they are built on non-primary key attributes, often for supporting queries on other fields. Example, search by employee department, etc. Secondary indexes can have multiple entries for the same key value if duplicates are allowed. So an example of this is if multiple employees are in the same department, you might create an index on the department attribute to speed up the query finding. Then the third type of indexes are clustered indexes, indexes that change the physical order of the data to match the index, ensuring data and index are aligned. Then moving on to the fourth type of index, which are non-clustered indexes, an index structure that does not change the data order but provides a separate reference for lookups. Now moving on to single level and multi-level indexes. Single level indexes. In this structure, there's only one level of indexing where each entry points to a block in the data file. If the number of records is small, a single level index will work. So an example of this is think of it as a table of contents where each entry points to a specific section of a book. Then multi-level indexes. When the dataset grows, a single level index can become very large and less efficient. This is where the multi-level indexing comes in. Multi-level indexing creates a hierarchy where one index points to other indexes, and basically it's like higher level indexes points to lower level indexes, which in turn points to data blocks. Then there is b beta minus tree and beta plus minus tree. They are also common for multi-level indexing. B minus trees, these are balanced trees that maintain sorted data and allow searches, insertions, and deletions in logarithmic time. Each node in the tree holds several keys and pointers to children. Then B plus minus trees, a variant of B minus trees where all the actual data is stored at the leaf nodes and the internal nodes only store keys for faster retrieval. This allows for range queries. So an advantage of these B trees are that they reduce disk input output operations by creating multiple level of index files. For very large databases, multi-level indexing can also ensure faster performances. So now let's move on to querying techniques. Querying techniques are essential for data retrieval. These techniques like indexing, parsing, and caching can significantly enhance query performance. Understanding these methods allow for better data retrieval and management. So there is query processing that is a part of this. Query processing involves the steps required to execute a high level SQL query and return the desired result efficiently. The database system translates the SQL query into operations that retrieve data from the underlying storage. Key steps in this include parsing, translation, optimization, execution. So let's start with parsing. In parsing, the SQL query is parsed to check for correct syntax and semantics. The database management system checks if the query is valid. The output of the parser is typically an abstract syntax tree or an AST, which represents the logical structure of the query. Translation: after parsing, the SQL query is translated into a lower level form, usually relational algebra or logical operators. This form is easier for the DBMS to optimize and execute. Then moving on to optimization, that this translated query goes through a series of optimizations to improve its efficiency. The optimizer looks at different ways the query can be executed and chooses the most efficient one. And at last, the execution. The optimized query plan is then executed by database engine. During execution, data is retrieved and any necessary computations such as joins and aggregations are performed. Then let's move on to indexing for performance. Indexing is a powerful technique that improves the speed of data retrieval. By creating an index, databases can quickly locate the required information without scanning the entire dataset, which can lead to enhanced performance and reduced query time. Partitioning data efficiently. Partitioning involves dividing a database into smaller, more manageable pieces. This can lead to improved query performance and easier database management. Proper partitioning strategies can enhance the overall efficiency of data retrieval processes. So, well, this is also a part of query optimization, which is one of the most important aspects of query processing. And the main cost is to reduce cost of CPU, memory disk, and input output. So there are two main approaches to this query optimization. First is the heuristic approach. Second is cost-based approach. So in the heuristic approach, we use predefined rules and principles to transform the query into an efficient form. Some include push selections and join reordering. Then the cost-based optimization. This method uses a cost model to estimate the resource usage of different query executions, such as CPU time and input-output cost. Then, uh, yes, so this is where the index and join operations lie. Index usage. Using appropriate indexes can reduce the time required to locate data. The optimizer looks for the best indexes and use for speeding up data retrieval. Then join optimization, the order and method of performing joins in SQL queries can greatly influence performance. Optimizing the join sequence or method, hash join, merge join, etc., can reduce execution times. Or materialized views, instead of recalculating results for frequently executed queries, a materialized view stores pre-computed results. This is useful for complex aggregate queries that would otherwise take a long time to compute. Then these are caching techniques. Caching techniques store frequently accessed data in memory for quick retrieval. By implementing caching techniques, organizations can significantly reduce response times and improve overall system performance, leading to better user experience. So now moving on to conclusion and key takeaways. In conclusion, efficient storage, indexing, and query optimizations are critical components of modern database systems. And by organizing these data in structured file formats using indexes for faster lookups and optimizing queries for resource efficiency, databases can handle large volumes of data while maintaining quick response times. Thank you.